Hi, I'm Mrs. Adams. This video will cover Lab 10 of SMU's Chem 1113. The lab is bonding and molecular geometry. Why is this important? Well, knowing the shape of a molecule can help us predict properties of the molecule, such as boiling point, melting point, solubility in water, and it also helps us learn how the molecule may react or interact with other molecules. In this lab, in part A, first we will draw the Lewis structure of a molecule. We'll count the bonding pairs and the lone pairs and determine the arrangement of pairs of the molecule. Then we'll select the molecular geometry associated with that arrangement of pairs, and we will determine the bond angles between the bonds, the bond polarity, the molecular polarity, and the hybridization of the central atom. In part B, we will calculate formal charges on two different structures that have been proposed for a molecule, and you will end up selecting the best structure based on some criteria that we have given in the lab manual. And in part C, we are going to draw resonance structures correctly, predict the arrangement of pairs, the molecular geometry, and the bond angles between the atoms. So we're going to start experiment 10. We're going to do experiment 10 in 3 parts. In the first part, in lab sheet A, we're going to draw the Lewis structure of the molecule, count the bonding pairs and lone pairs about the central atom. Then we'll find the arrangement of pairs. We'll determine the molecular geometry and draw the 3D structure. Then we'll find the bond angles between the atoms and the bond polarity, and also the molecular polarity. Finally, we'll note the hybridization of the central atom. In lab sheet B, we will be calculating formal charges and determining which structure of the two given is the better representation of the molecule. And in lab sheet C, we will draw the resonance structures of a molecule and then determine the arrangement of pairs, molecular geometry, and the bond angles between the atoms. All right, let's start off with arsenic tribromide. The first thing we are going to do is draw the Lewis structure. So we need to determine, first of all, is how many electrons are going to be in our molecule. Arsenic is in group 5, so it has 5 electrons in its valence shell, and bromine is in group 7. So it has 7 electrons in its valence shell. So let's calculate that number. We've got 5 from arsenic and 21 from bromine. That's a total of 26 electrons that we need to put in our structure. So I just will draw a general structure. This first one doesn't need to be the 3D depiction. We'll do that later. And this is described quite well. There's a stepwise procedure in the lab manual, and I'm just going to walk you through it. First, you put 2 electrons in each bond with the central atom. You can use X's, dots, or a line. And then you will fill the octet of the outer atoms. You'll count up the electrons now, and you'll find that there are 24 electrons in this structure that we've drawn so far. But we need 26 in our structure. So what do you do with those extra 2 electrons? You're going to put them on pairs as a lone pair on the central atom. So that's our Lewis structure. You can draw that in your space, in your box, on in the first line for this molecule. Now let's look at how many bonding pairs are about the central atom. I've got 1, 2, and 3. How many lone pairs are about the central atom? I've got 1 lone pair. I've got a total of 4 pairs right now. And any total of 4 means that there is a tetrahedral arrangement of pairs. And feel free to reference table 10.1 while you're working through this. You need to have a mastery of it for the exam, but feel free to refer to this frequently while you are going through this entire lab. You can see here that any arrangement of 4 pairs, whether it's a 4 and a 0, 3 and 1, 2 and 2, will always be a tetrahedral arrangement. Let's build the molecule now. I have selected a 4-hold molecule because right now I have 4 types of bonds that I need to use. Each of these will be a bromine atom, and this will be your arsenic atom. There's my 3 bromine bonds. And I'm going to use this small half sphere to depict the lone pairs. And there is the molecule that we have built. You can refer to table 10.1 and you can see that that molecular geometry is trigonal pyramidal. Let's look at that for a second. This, if you look at the faces on the 3 sides, that's trigonal, and it looks like a pyramid, okay? If you look in the table, again, you can look at all trigonal pyramidal molecules, the bond angle between the atoms, and I'm talking about between these atoms here, is less than 109.5. If it was a tetrahedral molecule without a lone pair, it would be 109.5 between the bonds. But since we have a lone pair, lone pairs take up a huge amount of space, and they kind of squish the remaining bonds together, and that's why it's a little bit less than 109.5. Let's look at the bond polarity between the bromine atom and the central arsenic atom. And this is kind of an easy way to do it. If they are different atoms, then there will be a slight electronegativity difference between the 2, and the bond between the 2 is polar. The electrons will spend a little bit more time closer to one atom than it will the other. So that this will be a polar bond. Now, let's look at the overall molecular polarity. And there's a little decision chart here that you can use. Is it an ion? And it is not. I don't see any superscript up here. If it is, you shade the square. Are the terminal atoms the same? Well, here I've got 3 bromines. Yes, they are. Does the molecule have lone pairs? Yes, it does. And is it the linear geometry of the trigonal bipyramidal or the square planar geometry of the octahedral? Nope, because we know it is the trigonal pyramidal geometry of the tetrahedral. Yes, or no, pardon me, that will be a polar molecule. And then for hybridization of the central atom, you need to look at the number of atomic orbitals. We have 4 total orbitals here. We've got 1 from the lone pair and 3 from the bonding pairs. And that gives you, we need to hybridize 1 s orbital and 3 p orbitals. We call that sp3. All tetrahedral molecules, no matter what combination of lone pair and bonding pairs they have, will always be sp3. And be sure you write that 3 as a superscript. Okay, let's move on to our next molecule. And that is gallium iodide. We're going to look at gallium, and that is in group 3. So it has 3 electrons. And iodine has 7. It's in group 7. For a total of 24 electrons. We're going to draw a skeletal structure of this molecule. And we're going to put 2 electrons in each bond and then fill the octets of the outer atoms. Now we can check to see if we populated all the electrons. We've got 24 electrons in our structure. We needed 24. The big question here comes up with, well, the iodine is fulfilling the octet rule, but what about gallium? Gallium, since it's in group 3, is an exception to the octet rule. It is very happy with just 3 bonds about it. Okay? So we look at our structure and we find that we have 3 bonding pairs and 0 lone pairs. You can refer to table 10.1, and any combination that adds to 3 will be trigonal planar. Now let's build this molecule. I'm going to select a 3-hold atom. There will be 1 for each bond. And then I have my iodine bonded to the gallium. And as you can see, it is trigonal and all of the atoms lie in one plane. The molecular geometry is also trigonal planar. And here we can draw the 3D structure of this also. And while I'm at it, I should draw the 3D structure of the one above it. I have arsenic in the middle. I have one bromine in the plane of the paper, one coming out, and one going back in to the plane of the paper, and a lone pair. The bond angles between the atoms of gallium iodide are 120, and the bond polarity between the iodine atom and the gallium atom, they are not the same. It must be a polar molecule or polar bond. And looking at the molecule, you can go back and ask yourself the same questions. Are the terminal atoms the same? Yes. Does the molecule have lone pairs? No. So this molecule is nonpolar. All the dipole moments in this molecule will cancel each other out. You can go back to your hybridization sheet and realize that any combination totaling 3 pairs or trigonal planar is sp2 hybridized. Okay, let's do our next one. Iodine trichloride. Both iodine and chlorine are in group 7. So I have 7 electrons from iodine, and from chlorine I have 3 of those. I need to populate my molecule with 28 electrons. I'll put the iodine in the center, and I'll put my chlorines around it. You put 2 electrons in each bond, and then fill the octets of the outer atoms. And at this point, when you count up, you have 24 electrons. We need 28 in our structure, so what do I do with the extra 4 electrons? You put them on the central atom in pairs. Now this structure has 28 electrons. We have 1, 2, 3 bonding pairs about the central atom, and 1, 2 lone pairs. The arrangement of pairs is trigonal bipyramidal. So let's build this one. I'm going to pick a 5-hold molecule because I have 5 pairs that I need to put in my molecule. I've got 3 bonding pairs. There's my chlorines, and 2 lone pairs. I'm going to leave that there for a minute. If you'll refer to table 10.1, this molecular geometry is T-shaped. See how that looks like a T. I want to build one that I frequently get, not occasionally, and I want to show what is an incorrect depiction of this molecule. I'll get this a lot. Does this look like a T? No, it does not. And we're going to look at this one that does look like a T. There are two positions in a trigonal bipyramidal molecule that the lone pairs or the atoms, the terminal atoms, can go into. And one is the axial position, the ones that are up and down, and there are three in the equatorial position, as if it was going around the equator of the molecule. In trigonal bipyramidal molecules, lone pairs, in order to minimize repulsion, like to be in the equatorial position. If you look at it in this molecule, I've got one lone pair in the axial position, and therefore this is a bad depiction. It's not going to look like the T that this one does. So when you're drawing this, I like to start with, this is a 3D, I like to start with the two atoms that are in the axial position. I'll add the third one in the plane of the paper, and then you'll have one lone pair coming out of the paper and one going back into the paper. The bond angles between these atoms are 90 degrees. The bond polarity between the chlorine and the iodine is polar. And the molecular polarity, you can go through this flow sheet again. Are the atoms the same? Terminal atoms the same? Yes, they are. They're chlorines. Does the molecule have lone pairs? Yes. Is it the linear geometry of the trigonal bipyramidal? Nope, it's the T-shaped. So this molecule is polar. And then if you refer to your hybridization, any combination of 5 pairs is a trigonal bipyramidal arrangement, and your central atom has sp3d hybridization. Let's do the last one on this sheet. We've got sulfur hexafluoride. Sulfur is in group 6, so it has 6 electrons, and fluorine is in group 7. (42) and 6 is 48 electrons. I'm going to put my sulfur in the center, and I'm going to put my fluorine atoms, my 6 fluorine atoms around it. You'll put 2 in each bond, and then fill the octets of the outer atoms. We'll count the electrons, and we have 6 times 8 is 48. I don't need to do anything else with this molecule. I have 6 bonding pairs and no lone pairs, And any combination that adds to 6 is an octahedral arrangement of pairs. So let's build that one. I'm going to select a 6-hold atom because I have 6 pairs. And there is my structure. I'm going to let you refer to the Table 10.1 and determine what your molecular geometry is. I'll help you draw it. I will put your molecular geometry there. You need to complete that by yourself. And again, I'd like to do the axial ones first. I've got 2 fluorines coming out of the plane of the paper and 2 going back in to the plane of the paper. I'd like you to determine the bond angles between these atoms. You can refer to Table 10.1. And what about the bond polarity between a fluorine and a sulfur? That is going to be polar. And I'd like you to determine the molecular polarity. Okay, you can ask your question, are the terminal atoms the same? If they are, does the molecule have lone pairs? Yes and no. And then complete this to determine if that molecule is polar. And for the hybridization of the central atom, all octahedrals are sp3d2. Our next molecule is xenon tetrafluoride. Xenon is a noble gas in group 8, so it has 8 electrons. Fluorine is in group 7 with 7 valence electrons for a total of 36 electrons that we need to put in our structure. I'll put xenon in the center and put my fluorine atoms around it, and then continue on with our stepwise procedure for putting the electrons in our structure. So I filled the octets of the outer atoms, and I have 32 electrons. I need 36 in my structure, so I'm going to put them on the central atom in pairs. I'll let you figure out for this one how many bonding pairs and how many lone pairs there are. This is an octahedral arrangement. And it is a square planar molecular geometry. So let's build that. I'll select a 6-hold molecule. And I will put my fluorine atoms in, and then my lone pairs. Lone pairs like to go in the axial. Here's the axis, up and down, in the axial position of octahedral molecules. you can see that this makes a square and all the atoms are in one plane. And we can draw the 3D structure of that. Xenon. In the center, I'm going to have one fluorine coming out of the page on this side and going back into the page, and on the other side I will have the exact same thing. The bond angles between the atoms is 90 degrees, and I'd like for you to finish out this row with the bond polarity, the molecular polarity, and the hybridization. Our next molecule is selenium difluoride. Let's look at that one. It might be a very familiar molecular geometry when we're all done. Selenium is in group 6, so it has 6 valence electrons. And fluorine is in group 7, so it has 7 valence electrons. I've got 14 plus 6. I have 20 electrons that I need to populate in my structure. I'm going to put selenium in the center and my fluorines around it and start populating my structure. I have 16 electrons. I need to have 4 more in my structure, and I'm going to put them in pairs on the central atom. I'd like to point out here, frequently I will get this. I'll abbreviate this way. And this is not my favorite way to see a Lewis structure for this arrangement and molecular geometry. It may give you the impression that it is a very linear and nonpolar molecule, but we're going to find out this is one of the most polar molecules around. This molecule has 2 bonding pairs and 2 lone pairs, and I'm going to let you figure out what these are, although I really would like to draw this structure for you, the 3D structure. You've got selenium in the middle, you've got 1 fluorine coming out of the page, 1 fluorine going back into the page. And we've got a lone pair going back into the page and 1 in this plane of the paper. I'm going to pick a tetrahedral molecule, attach my fluorines to it, and attach my lone pairs to it. And as you can see, this is a very not linear molecule at all. So that's why this is a very poor description of this molecule. The bond angles are going to be less than 104, or about 104.5 degrees, and I will let you finish the remainder of this line. What molecule does that look like? How about water? One of the most polar molecules. Let's do our next one. Carbon dioxide. Carbon is in group 4, so it has 4 valence electrons, and oxygen is in group 6 with 6 valence electrons. I've got 12 plus 4 is 16 electrons that I need to put in my structure. I'm going to put carbon in the center and oxygen's about it, and then start populating my structure with electrons. I've done that, and when I count, there's 16 electrons there, which fulfills the amount that I need. This oxygen fulfills the octet rule. This oxygen fulfills the octet rule. But carbon, which must fulfill the octet rule, only has 2 bonds associated with it, and we know it needs 4 or 8 electrons. So what you're going to do is you're going to take one at a time and move electrons from the lone pairs around the central atom into bonding pairs, of the terminal atom into bonding pairs with the central atom. And I'm going to have to do that twice. So this molecule has 2 double bonds, where a double bond represents 4 electrons. Let's build this one. I'm going to make a double bond and show that it's a double bond using these longer bonds, very flexible ones that I have. And you'll see that it is a very linear molecule. I have 2 bonding pairs and no lone pairs. Let's talk about that for a second. Vesper theory treats single, double, and triple bonds as one bond. So I'm counting 1, 2 bonds. The arrangement of pairs is linear. And I'll let you figure out the molecular geometry and draw the 3D structure of that. The bond angles are 180. The bond polarity between the carbon and the oxygen is definitely polar, but let's look at the overall molecule. The terminal atoms are the same, and there's no lone pairs. This is a nonpolar molecule. And all linear molecules are sp hybridized. The last one on this sheet is an ion, NO2 minus. Nitrogen is in group 5. It has 5 valence electrons. Oxygen is in group 6. It has 6 valence electrons. And I've added 1 extra electron because of the charge. I have a total of 12, 17, 18 electrons I need to put in my structure. I'm going to start with a structure and then put 2 in each bond, and then fill the octets of the outer atoms. This is 16 electrons. I need 18, so any extra ones go as a lone pair on the central atom. This oxygen fulfills the octet rule. This oxygen fulfills the octet rule, but this nitrogen does not, and it must. So it doesn't matter which one you pull from. You're going to take one pair and move it in to the bond between the central atom. Since this is an ion, in your Lewis structure, you need to bracket it and put the ion charge as a superscript. We'll see that it has two bonding pairs, 1, 2, and again, Vesper does not care whether that's a single, double, or triple. It's counted as one bond and one lone pair. Any combination adding up to 3 is trigonal planar. I want you to determine the molecular geometry and the 3D structure. And let's build it. Here's my single bonded oxygen. Here's my doubly bonded oxygen. And here is my lone pair. I'll let you determine the bond angle between the atoms. Remember, it has a lone pair, so it's got to be less than what is listed for a trigonal planar molecule. You know that your bond must be polar, and the molecule, you might say it's polar, but since it's an ion, all ions are going to be polar. So I shade the box just for this one. And I'll let you determine the hybridization of that nitrogen atom in this structure. The next molecule is chloroform, trichloromethane, and I'll let you determine the Lewis structure for that. You'll find that it has 4 bonding pairs and no lone pairs about the central atom. I'll let you determine much of this. But let's build this molecule. I'm going to select, because I have 4 total pairs, a 4-hold atom. And I've selected the hydrogen atom to be green and the 3 chlorines white. I'll let you fill the rest in, but let's look at the molecular polarity here. This is a fairly easy one. Are the terminal atoms the same? No. This is a polar molecule. Okay, let's move on to the next one. Selenium tetrafluoride. This is actually my favorite geometry. Selenium is in group 6. It is 6 has 6 electrons in its valence shell, and fluorine is in group 7. When you add these together, 28 and 6 is 34 electrons that we need to put in our structure. I'm going to make a typical structure, selenium in the center with fluorine around, and again we're just populating our structure with our electrons. When we count our electrons, we're going to find that we have 32. We need 2 extra ones. We'll put them on the central atom as a lone pair. This is a 4 and 1, and I will let you figure out what the arrangement of pairs is. This is a seesaw geometry, so let's build that. Since I have 5 total pairs, I'm going to pick a 5-hold molecule, and here's the seesaw geometry. Let's be sure we draw this one correctly. Remember, in trigonal bipyramidal molecules, draw your axial ones first. Then draw one of the equatorial fluorines. The other one can come out of the paper in the equatorial position, and so can the lone pair going back into the paper. I'll let you determine the rest of this. Frequently, I also see this arrangement or built in correctly. Where somebody will put the lone pair in the axial position, and that is definitely not a seesaw. Okay, so this is the bad depiction. Remember, lone pairs go in the equatorial position around the equator of the central atom. Let's do the next one. Iodine pentafluoride. I will let you draw the Lewis structure. And it is a 5 and 1. 5 bonding pairs, 1 lone pair. So let's build that. I'm going to select a 6-hold molecule. And I'm going to be very careful to put my lone pair in the axial position, because for octahedral molecules, the lone pair needs to go in the axial position. Okay, the one that's straight up and down. I'll let you determine the molecular geometry and the 3D structure, as well as the bond angle between the atoms, the bond polarity and the molecular polarity, and then hybridization. All right, our next one XeF2. Let's do that one. Xenon is in group 8. It has 8 valence electrons. And fluorine is in group 7. 14 plus 8 is 22. And you'll follow your stepwise procedure, populating your structure with electrons, and you have 16 electrons. I have 6 extra electrons that I need to put in my structure. So I'm going to put them as pairs about my central atom. I'll let you determine how many lone pairs and how many bonding pairs. This is a trigonal bipyramidal molecule. So let's build that. And for trigonal bipyramidal molecules, remember that lone pairs must go in the equatorial position. So the first thing I do is put my 2 fluorines in the axial position. And you can see that this is a very linear molecule for the molecular geometry. And I will let you draw that. Remember that your fluorines will go in the axial position. I'll let you do the bond angle between the atoms and the bond polarity, as well as the hybridization of the central atom. But let's determine whether this molecule is polar or not. Is it an ion? No. Are the terminal atoms the same? Yes. Does the molecule have lone pairs? Yes, it has 3 of them. Is it the linear geometry of the trigonal bipyramidal? Yes, it is. This is a non-polar molecule. And let us do the last one in part A. And I have got C2H4. Let's look at this one. And we're going to finish most of this for one of the central atoms. So I've got carbon is in group 4. I've got 2 of them. I've got 4 electrons in its valence shell, and hydrogen has 1 electron. I've got 10 electrons that I need to put in my molecule. I'm going to set it up like this. I'm going to first put 2 in each bond. And then hydrogen is just fine with 2. Don't go making an octet out of that. We still have 4 electrons that we need to populate. Well, I guess I can put them right there. Hydrogen is fine with 2. This carbon has 6, it needs 8. This carbon has 6, it needs 8. And this hydrogen is 2, and that's fine. So we're going to take them and put them in the center. And this still has 6. This one now has 8. Now this carbon has 6 plus 2 is 8. This carbon has 6 in the triple bond plus 2 is 8. Here's another way to depict this molecule. And remember, Vesper theory treats this triple bond, 6 electrons, as one bond. And I'm only going to look at perhaps this central atom. It's got 2 bonding pairs and 0 lone pairs. So let's build it. And I'm just making the triple bond here. You can see the triple bond, 1 bond, 2 bonds for a 2 and a 0. Each carbon atom, and we're only dealing with the left one right now, it's going to be the right one right now, it's going to be the exact same for the left. Linear and linear. I'll let you draw the molecular geometry of this. And also, I'd like you to do the bond angles between the atoms. I just want to look at bond polarity for a minute. This one is a little bit tricky. What about the bond between the carbon and the hydrogen? That one, I would say, is polar. What about between the carbon and the carbon? That's the same atom. There will be no difference in electronegativity. That bond is nonpolar. I'll have you look at the molecular polarity, do that by yourself, and the hybridization of the central atom. If it's linear, it will be sp. We've just completed everything for part A. Anything that's in pink, please fill out yourself. In lab sheet B, you will be given 2 cards, and each card has 2 possible structures of a molecule on them. And we'd like you to calculate the formal charge on each atom and each molecule, and then using the description in the lab manual right after the formal charge section, we need you to select which structure should be the preferred structure. I'm just going to go over with the top one how to calculate formal charge. Formal charge is equal to your valence electrons minus half of your bonding electrons minus your non-bonding electrons. So the first thing you need to do is to draw in any lone pairs that would exist in this molecule. Hydrogen will not have any. Carbon has 8 electrons, it won't have any. Nitrogen has 8, it won't have any. And this one needs 8, but I only see 4. I am going to draw 2 lone pairs on this nitrogen. Let's calculate the formal charge on this hydrogen. And I'll just do hydrogen left. Valence electrons, I have 1 minus half of the bonding electrons, 1, because I've got 2 in that bond, and minus 0 for non-bonding electrons. That is 0. Let's do the top one. It's going to have the same thing. 1 valence, 1 from the half of the bonding electrons, and no non-bonding electrons. That also has a charge formal charge of 0. Carbon, I have 4 valence electrons minus 8 electrons in the bonding. Half of that is 4 minus 0 for non-bonding is 0. Nitrogen, the left one, nitrogen is in group 5. It has 5 valence electrons minus half of the bonding electrons, 4 minus 0 for non-bonding electrons. That is a +1. This nitrogen, 5 minus 2 minus 4 is equal to -1. This one has -1. You can do a little check here. These must add up to the total charge on the molecule, which is 0. You'll do the same for this structure, and then using what is in the discussion in the lab manual, again the section right after the formal charge example, it says there are 2 ways to determine which is the best structure. I need you to read that and to select which one of these is the best structure. You'll do the same with card 9 for the lower half of the sheet with these 2 molecules. Determine the formal charge and then refer to the discussion section to select which one of these is the preferred structure for this molecule. In lab sheet C, you need to draw the correct resonance structures using the correct brackets and the arrows, and then if the structure is an ion, please include the charge as a superscript outside the bracket. After this, we'll determine the arrangement of pairs, the structure, geometry, and then the bond angles between the atoms. Let's do the first one together. Here is one structure. It is an ion. So I'm going to put it in brackets with the charge of the ion as a superscript. I'm going to do the resonance arrow, and this structure could also be depicted as this, where the double bond is on the right oxygen instead of the top oxygen. Again, this will be in brackets with a superscript charge of the ion. This arrangement of pairs, since I have 3 bonds, is trigonal planar. The structure geometry is also trigonal planar. And the bond angles between the atoms is 120 degrees. Complete the next 2 with the arrangement, structure, and bond angles for each one of them, and be sure you use the correct arrow. And in number 2, it is an ion, so be sure to put the ion as a superscript.